going here. We've got most of us in here, missing just a few folks, but hopefully they're logging in as we speak. I don't know, but we hope so. We'll see. All right. Well, we're going to get started. And we've got, let's see, 25 of us here. Let's take a look and see what wonderful things our curriculum holds for us this week. Okay, looking at our grade screen as usual, the place you should always start. If you don't know what's due this week or if you're missing anything, go to this grade screen. You can find it right there, or you can find it by going to the menu and going to grades. So if we go to the grade screen, we go down and let's see. September 29th was this past Sunday that we just finished. And you had two things due, 2.03 and 2.04 quiz. So we had one lesson last week and the quiz. Those were both due Sunday night. So if you didn't get that turned in by Sunday night, then you should see you won't have anything here under some. This is when you submitted it. Check mark says it's done and your grade should be here. So if you're missing anything, there you go. This week, October 6th is this Sunday. So we have 2.06 and 2.07. So complex numbers and operations on complex numbers. So those go well together. We're going to talk about complex numbers. What is a complex number? And then how do we use it with operations? So 2.06, 2.07. Then you see next week we have a lesson in the practice test. And then we'll be part 1 and part 2 of the test coming up on October 20th, right around our fall break. We'll get a fall break there for a day or two. But let's look at 206, 207 this week. We have a little extra video that goes with this too. 2.06, complex numbers lesson. All right, we're going to learn what causes the need for imaginary numbers and what types of parts are necessary for a complex number. So to start out, we really should review before we start getting into complex numbers. Shouldn't be necessarily news. You might have heard of complex numbers before, but if you haven't, we're going to get into it now. So let's look at classifying the real numbers first of all. So in your math studies over the last however many years, 8, 9, 10 years of math, you learn this starting back in elementary school at the beginning. Natural numbers. That was some of the first numbers you learned. It is the first numbers you learned. Natural numbers. 1, 2, 3, 4. 0 is not a natural number because generally our natural numbers evolved from like having sheep or having cattle and needing to give a quantity to how many you owned. And so you didn't start with 0. If someone didn't have sheep, you didn't say, hey, you have 0 sheep. That's not how numbers started. They started with saying, let me see how many sheep I have. 1, 2, 3, 4. And so that's the natural numbers. That's where we started as a civilization with numbers. Then we added whole numbers. That's when we got the concept of, it could include 0 because if I sell them, and I am a sheep farmer, and they're like, how many sheep do you have? Well, I have 0 right now because I sold them all. I got to buy some more. So it's just like the natural numbers, but it adds 0. That's the only difference. 0, 1, 2, 3, 4. And then from there, after we learn that, we're starting to get up in our elementary years in school, and we learn about integers. So integers include all the whole numbers, 0, 1, 2, but it also includes the negative whole numbers. -2, -1, 0, 1, 2, all of those, that's the integers. So integers can be positive or negative, but they do not include any fractions or anything like that. From there, see, every one of these groups includes the group in front of it. So all the natural numbers are part of the whole numbers. All the whole numbers are part of the integers. All the integers are part of the rational numbers. And that's any number that we can express with a fraction. Rational comes from the word ratio, and a fraction is a ratio. 3/4, 1/6, 1/2. Those are ratios. So rational numbers include all the integers, all the negative numbers, include 0, all the positive numbers, and all the fractions. 7/12, anything like that. Then we have, and this is a totally separate group, because we have rational numbers and we have irrational numbers. So everything above is part of the rational numbers. And if it's not a rational number, then it's an irrational number. It's just two separate groups. That's any number that cannot be expressed as a fraction or expressed as a rational number. And you're like, what number can we now express as a fraction? Well, pi, for one. Pi is, you can't write that as a fraction. The square root of 2 is not a fraction. 3.12428583617 ... We can't write that as a fraction because it does not end. It continues on and on and on. Anything we can put as a fraction either repeats or ends. Some numbers fall into more than one category. So let's see. So it gives us a little quiz. Drag each number into the box if it fits within the category. Numbers can belong to multiple categories. Okay, so 5. Is 5 a natural number or a non-natural number? Well, if we could count sheep, remember natural numbers come from counting things. 5 is something we can count. 0 is not a number we can count. It's not natural. -3. We don't have -3 sheep. Hopefully we don't have 2/3 of a sheep. That's not a natural number. We do not have -1/7 of a sheep. We do not have the square root of 3 of a sheep. So that's how natural numbers are. I just think, can I count that? We don't have pi number of sheep. We do not have 2.713. 5 was the only natural. So then you can go and say, okay, what about whole numbers? Well, that's easy. 5 is a whole number. 0 is a whole number. -3 is a whole number. Oh, I'm sorry. Whole numbers are not negative. 2/3 is not a whole number. That's only 2/3 of a number. -1/7. Square root of 3 is not a whole number. Pi is not a whole number. This is not a whole. So it's just 0 and 5. And it goes on. Integers. That's anything that does not have a fraction. It includes decimals. So everything that is not. Getting easier and easier because more things fit. Rational or irrational. Anything we can rise a fraction. 5 we can rise a fraction. 5 over 1. 0 over anything. -3. 2/3. -1/7. Square root of 3, no. Pi, no. That has ... which means it doesn't end. So there you go. Nice review. To better understand the real number system, here everything fits inside the other one. See, natural numbers are inside the same circle as whole numbers, which is inside the same square as integers, which is inside the same hexagon as rational numbers. And then irrational numbers are separate, but they all fit in the real number system, the big green rectangle. So that's a nice review of numbers. Now we're going to talk about numbers that are totally outside of the real number system because they're imaginary numbers. What pair of identical factors produce -1 when multiplied? What can you multiply by itself to get -1? You're like, oh goodness. Well, 1 times 1 is 1. -1 times -1 is also 1. They're not -1. To solve this problem, the concept of imaginary number, I, is what we call it, I. That's the name of the imaginary number. It's the letter I. So I equals, oh, we're going to put this in our notes. I equals the square root of -1. I is imaginary. Put number. I is an imaginary number. It is the square root of -1, which, oh, my light not on. Yeah, there it is. Square root of -1. Not a real number. It's not part of the real number system, but we're going to use I and do a lot of calculations with it. And if you square it, here's an interesting thing. let's look at these because we're going to have this in our lesson. I squared, that is the square root of -1 times the square root of -1, right? That's what it means when you square something. So that is the square root of -1 squared. And as we know, if you square a square root, those cancel each other out. So I squared is a real number. It's -1. Because that's what's happened when you square I. You take it times itself. So this is imaginary. This is not. I squared is not imaginary. Now we're in the real number system. All right. History of the imaginary number. Oh, let's take a look at that. So up to this point in your math education, you've been working with numbers in the real number system. So you're about to discover there are numbers outside the real number system called complex numbers. What makes these numbers special is the existence of imaginary numbers. So you're like, why do I need to know about numbers that don't really exist? Why would I care about that? Well, they do exist. The term imaginary is thought to be really, it's a bad name. It's an unfortunate title for them. So secondly, why do you need to know about these numbers at all? Well, throughout history, there have been times when some mathematical construct was invented, but they didn't really have a purpose for it. It's like we know the Pythagorean theorem, a squared plus b squared equals c squared, even if they didn't know where exactly it worked. Early man knew of the concept of 1 before he knew about 0. 0 did not exist till later. Numbers at the time were used to count sheep and other animals as a source for food. There's no need to define the concept of 0. When fractions were first defined, they were thought to be useless. Why would I ever use 1/2? What in the world? I don't have half a sheep. I don't have half a cow. I don't have half a camel. But what purpose could there be between having a number between 0 and 1? So today we use fractions all the time, especially in recipes. You need 2/3 of a cup of water. You need half a cup of flour. We use it all the time. Fractions are a regular part of that. Money, a lot of things don't cost $1. They cost $1.5 or $1.75. That's $1.75, right? $1.75. Telling time, it's half an hour past 2 o'clock or something. So the concept of imaginary numbers has a similar type history. When we solve an equation like x squared minus 9 equals 0, right? We can do that. X squared minus 9 equals 0. We can solve that. You got to move the 9 to the other side. You get x squared equals 9. And then you take the square root of both sides. So x equals plus or minus 3. So let's play with that a little bit in our paperwork here. So yeah, when we started out, we'd say x squared minus 9 equals 0. Move the 9 to the other side. X squared equals 9. We take the square root because we're trying to get x equals. So the square root of x squared is x. The square root of 9 is plus or minus 3. And we said, okay. And the reason there's two answers is because 3 times 3 equals 9. And -3 times -3 also equaled 9. So either one of those could be the right answer. But what happens when we get here, when we were doing another math equation where we had x squared plus 1 equals 0, we said, okay, well, we have to get x by itself. So we got x squared equals -1. Square root of both sides, we've got x equals plus or minus the square root of -1. That's not even a real number. But math led us to this before we even knew what good are imaginary numbers. Because the square root of -1, when I square it, I do get x squared. There's got to be a purpose for that in math. All right, so you begin just like the last equation. You get there where you get square root of -1. So let's try to simplify the square root of -4. Oh, that's a good thing to work in there. Because we're going to need to be able to do this. we're going to be able to need to do this. The square root of negative 4. We can simplify that. Because anytime you have a number underneath a radical sign, you can rewrite it as this. The square root of negative 1 times the square root of 4. Or actually, we could have written it like this first. Square root of negative 1 times 4. Right, these are all three the same. Square root of negative 4 could be the square root of negative 1 times 4, which we can break apart as the square root of 1 times that. So when we take that one step farther, times 2, because the square root of 4 is 2. And now we know this has a name. The square root of negative 1 is I. So it actually equals 2I. That's what the square root of negative 4 equals, 2I. 2 times that imaginary number, which is the square root of negative 1. See how they did it with their sample. Okay, so they said the square root of negative 4 is the same as the square root of negative 1 times the square root of 4. Square root of negative 1 is the same as I. So it's I square roots of negative 4. And the square root of 4 is 2. So the answer is 2I. So they got the same thing, 2I. Okay. So that was the history of an imaginary number there. But isn't I a variable? Not for the purpose of this course. I, and it's written in italics, it's right slanted, is always the imaginary number square root of negative 1. All right, so we have a video to see here. So let's see what we're going to learn in this video.
In this problem, you are asked to simplify the square root of negative 8. Begin by factoring the imaginary number from the radical. Rewrite the square root of negative 8 as the square root of negative 1 times the square root of 8. The square root of negative 1 is equal to I, so you can rewrite this as I times the square root of 8. Since the square root of 8 is not in simplest form, rewrite it as a product of its perfect square factor, 4 and 2. So now you have the product of I times the square root of 4 multiplied by the square root of 2. Now you can simplify the square root of 4 as 2. Like coefficients of variables, typically the whole number is written before I, so the final simplified expression is written as 2I times the square root of 2.
There it is. So we have to simplify the 8 as well. We take out the imaginary part, but then the square root of 8, we can change that to square root of 4 times square root of 2, and we know what the square root of 4 is. So simplifying is somewhere where you may struggle a little bit if you haven't thought about it in that way. Let's look at another example. I'm going to do this one on paper so we can see better what it's showing us. So let's just do that right here because we're going to use up a lot of paper, I think. The square root of negative 45. So this is the same as the square root of negative 1 times the square root of 45. Right? We know the first step. That's pretty easy. We can break out the negative 1. Anyway. So square root of negative 1 is I. 45, if we think about is there any perfect squares that we can use to make 45? Yeah, that's the same as the square root of 9 times the square root of 5. 9 times 5 is 45. So this is the same as I times the square root of 9 times the square root of 5. Well, we know what the square root of 9 is. We can simplify that. It's a 3. So we can say it's 3I. And square root of 5, that's as simple as it gets. 5 is not a nice square number, so we can't take a square root of it. It's a decimal, 2 point something. And we can't pull any other factors. 5 and 1 is the only factors of 5. So this is our final simplified answer. If we want to know the square root of negative 45, it's 3I square roots of 5. Notice this is an imaginary number because there's an I in it. But that is how we simplify that number there. Let's go back. They took I square roots of 45, and then when you simplify it, 3I square roots of 5. That's what we got. Now, if you have a problem that you're working and you get it down to this point and don't know how to simplify it here, you'll get most of the points. You might miss 1 point for not simplifying it, right? But go ahead and show it, work it as far as you can. If you don't think it simplifies anymore, there's stop there. Or if you don't know how to simplify it, at least get to the right answer. This is the right answer, but it's not the most simplified. We should pull out anything we can pull out. Page 2. All right, here's where we talked about I squared, because that's the same as square root of negative 1 times the square root of negative 1. So it uses an example that if you had the square root of 3 squared, that's the same thing as the square root of 3 times the square root of 3, which 3 times 3 is 9. So it's the same as the square root of 9, which equals just 3. Well, that's what it started in here. You had a square and a square root, so they canceled each other out and left you with just the 3. So when you have a negative 1 with a square and a square root, we have a square and a square root, they cancel each other out. So I squared equals negative 1, which is a real number. And we will use this a lot because we want to get to where we can get rid of the imaginary part. So I squared is a real number. So with that, let's look at I to the third. I to the third is I times I times I. So let's put that in our notes because we it's good to have this information in our notes because we will use this all the time. I to the third equals I times I times I. Well, I times I is I squared, right? That's I squared. And we know I squared is negative 1. So this is negative 1 times I. And we know I is this. So this is the same as negative square root of negative 1. Because it has a negative 1 coefficient, and I equals the square root of negative 1. So this is what I to the third equals. The negative square root of negative 1. I to the fourth is I square, I times I times I times I. So look, we have 2 I squareds being multiplied times each other. Because I times I is I squared, which is negative 1. This I times I is I squared, which is negative 1. So that's negative 1 times negative 1. Negative 1 times negative 1 is a positive 1. So looky there. If we get an I fourth, I to the fourth, that just equals 1. That's a real number. This is a real number. I squared equals negative 1. I to the fourth equals positive 1. The only ones that end up imaginary numbers is the first and third. Now here's the really cool thing. There's a pattern here. I squared, I third, I to the fourth. What about when we get I to the fifth? That's I times I times I times I times I. Well, we know I to the fourth is 1. So I times I times I times I. This all equals 1 times I. So it's just I, which is just the square root of negative 1. Well, that's the same as just I to the first. So anytime you get bigger than 4, you're going to be able to pull 4 of those out and make it a 1. So I to the fifth is the same thing as I. I to the sixth, I times I times I times I times I. This is just 1. This is I squared, which is negative 1. So look at there. I to the 6th is the same thing as I squared. It's starting over. 5th is the same as the 1st. The 6th the same as the 2nd. Guess what the 7th is going to be the same as? I to the 7th equals I to the 4th times I to the 3rd. I to the 4th is 1, so it just equals I to the 3rd negative square root of negative 1. I to the 8th is I to the 4th times I to the 4th. So that just equals 1, because it's 1, it's 1 times 1, which is just 1. So it's the same as I to the 4th. I to the 3rd, I to the 4th. So every time it just repeats this pattern over and over again. I to the 1st, the 2nd, the 3rd, the 4th, I to the 5th, I to the 6th, I to the 7th, I to the 8th, I to the 9th, I to the 10th, I to the 11th, I to the 12th, 13th, 14th, 15th, 16th, and just keep going. So thinking about that, if we have I to the 26th power, I to the 26th power, how many 4s are there? If we divide it by 4, 26 divided by 4 is 6.5, which means we can take 6 4s out of that. 6 times 4 is 24. So the first 24 of those we could ignore because they equal 1. Because it means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20, 21, 2, 3, 24. So the first 24 of them just equal 1. They go away. So this is the same as I to the 2nd power. So it's negative 1. It's I to the 2nd power. I to the 26th is the same thing as I to the 2nd, which is negative 1. Which is nice. That's not an imaginary number. So that's what we're looking for, is patterns like that with I. I to the 5th. See, here's a little chart. It shows the same thing. I to the 1st, 2nd, 3rd, 4th is the same as the 5th, 6th, 7th, 8th, is the same as the 9th, 10th, 11th, 12th, is the same as I to the 13th, 14th, 15th, 16th. I, negative 1, negative I, and 1. I, negative 1, negative I, and 1. So you don't have to memorize it. Say here they did the 27th, which is close to what I did. Divide it by 4. That means 6 times. You're going to go through that. So subtract that. It's going to be the same as I to the 3rd. Negative I. Complex numbers. All right, let's take it a step farther. A complex number has 2 parts. Oh, we want to put this in our notes here. Let's say complex numbers. Complex numbers. All right. So a complex number can look like this. Let me give you an actual number instead of just using all variables. Let's say 12 plus 3i. That's a complex number. A complex number has 2 parts. 2 parts. So there's this part and this part. This is the real part. Right? Because 12 is a real number. That's a real number. We're talking about the actual number 12. But this part over here is the imaginary part. Three I is not a real number because that's 3 times the square root of negative 1, which we know does not exist. So it's imaginary. So complex numbers have 2 parts, a real part and an imaginary part. And that's important to understand when we start using complex numbers in our math, which we will be doing today. So real part, imaginary part. Real number 7, imaginary number 10i. All right, so this wants to know which of these numbers is a real part and which of these are an imaginary part. That's good practice for you right there. But it all breaks down to, is 3 a real number or is 3 an imaginary number? Well, 3 obviously is a real number. We've used it since first grade, probably kindergarten, maybe preschool. -6i. We've never counted with -6i. That's an imaginary number. 2, 7. Anything with an I is going to go over here, right? Because that's not real. Anything that doesn't have an I, that's the real part of the number. Don't make that hard. That is really that easy. It is really, really, really simple to know which part of the number is real and which part's imaginary. But when we put them together, those are called complex numbers. And that's the end of this lesson. Look, there's a lesson summary. A complex number consists of 2 parts, a real number term and an imaginary number term. And an imaginary number is defined as I equals the square root of -1. And then it talks about simplifying. If you have the square root of -45, you separate it to -1 times 45 so that you can change this to I, because that's what I equals, square root of -1. And then you simplify the square root of 45. So you end up with 3i squared to 5. And then there's that repeating pattern. I to the first, the second, the third, the fourth, and it wraps around. 5th, 6th, 7th, 8th. I to the 27th is the same as -I because it repeats around 6 times, and then the 7th time through, 25th, 26th, 27th, it's the same as I to the 3rd. Okay, there's some practice problems with. If you're like, okay, this is very confusing, then you should do this practice. What is the square root of -64? Well, we know the square root of 64 is 8, and the square root of -1 is I, so the answer should be 8i, because 8i times 8i will give us 64i squared, which would be -64. So if we square that, we'll end up with -64. So that must be the square root. Submit, yes, 8i. So there's a few of these you can practice. What is the square root of -100? Well, 10 times 10 is 100, and you got that I. All right, so look at those 5. Try those. Here's the second one. Items will disappear when they're stored. So what is I to the 5th the same as? Well, 1st, 2nd, 3rd, 4th, 5th gets us back to the beginning. It's the same as I. I squared, remember, equals -1. I to the 7th. I to the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th. I to the 7th is going to go as -I. 20th. Divide 20 by 4, you get an even number of 5. Same as there. So you can practice those. There's more. So get those. Here's some more practice problems on page 5. Simplify that. What's the answer? There's 5 questions down there. All right, let's look at the assignment that goes with this one. This will be pretty simple. Oh, wait. Yep, let's do this video first before we look at the assignment. A conjugate. Okay, let's talk about a conjugate right now. All complex numbers have a conjugate, which kind of means it's its partner. They don't exist by themselves. Imaginary numbers come in pairs. If you said, I'd like an imaginary number, please, you'll get 2 of them because they come in pairs. It's like you can't just buy one pizza. You have to buy a pizza and get a pizza free. That's the only way complex numbers come. So complex numbers come in pairs. And why is that? It's because the square root of -1 has a plus and a minus, right? If we could take the square root of -1, when we take the square root of +1, it's +1 and -1. It's a plus and a minus. So that means they come in pairs because there's a positive complex number and a negative complex number. So let's look at this video that explains this a little bit and see if that helps us understand how the conjugate is found. And it's very, very simple. Don't make this hard either.
We're asked to find the conjugate of the complex number 7 minus 5i. And what you're going to find in this video is finding the conjugate of a complex number is shockingly easy. It's really the same as this number. I should say be a little bit more particular. It has the same real part. So the conjugate of this is going to have the exact same real part, but its imaginary part is going to have the opposite sign. So instead of having a negative 5i, it will have a positive 5i. So that right there is the complex conjugate of 7 minus 5i. And sometimes the notation
We could almost stop the video right there because that's how you find the conjugate. You just change the sign on the imaginary part. But we'll continue because he's going to give more explanation.
for doing that is you'll take 7 minus 5i. If you have 7 minus 5i, 7 minus 5i, and you put a line over it like that, that means I want the conjugate of 7 minus 5i, and that will equal 7 plus 5i. Or sometimes someone will write, you'll see z is the variable that people often use for complex numbers. If z is 7 minus 5i, if z is 7 minus 5i, then they'll say the complex conjugate of z, and you put that line over the z, is going to be 7 plus 5i. Now you're probably saying, okay, fairly straightforward to find a conjugate of a complex number, but what is it good for? And the simplest reason, or the most basic place where this is useful, is when you multiply any complex number times its conjugate, you're going to get a real number. And I want to emphasize, this right here is the conjugate. 7 plus 5i is the conjugate of 7 minus 5i. But 7 minus 5i is also the conjugate of 7 plus 5i for obvious reasons. If you started with this and you changed the sign of the imaginary part, you would get 7 minus 5i. They're conjugates of each other. But let me show you that when I multiply complex conjugates that I get a real number. So let's multiply 7 minus 5i times 7 plus 5i. And I will do that in blue. 7 minus 5i times 7 plus 5i. And remember, whenever you multiply these expressions, you really just have to multiply every term times each other. You could do the distributive property twice. You could do something like FOIL to remind yourself to multiply every part of this complex number times every part of this complex number. So let's just do it any which way. So you'd have 7 times 7, which is 49. 7 times 5i, which is 7 times 5i, which is 35i. Then you have negative 5i times 7, which is negative 35i. You can see the imaginary part is canceling out. Then you have negative 5i times positive 5i. Well, that's negative 25i squared. And negative 25i squared, remember, I squared is negative 1. So negative 25i squared, let me write this down. Negative 5i times 5i is negative 25 times I squared. I squared is negative 1. So negative 25 times negative 1 is positive 25. And these two guys over here cancel out, and we're just left with 49 plus 25. See, 50 plus 25 is 75. So this is just 74. So we are just left with the real number 74. Another way to do it, you don't even have to do all this distributive property. You might just recognize that this looks like this is something plus something times, or something minus something times that same something plus something. And we know this pattern from our early algebra, that a plus b times a minus b is equal to a squared minus b squared, is equal to a difference of squares. And so in this case, a is 7, a squared is 49, and b in this case is 5i. B squared is 5i squared, which is 25i squared, which is negative 25. And we're subtracting that. So it's going to be positive plus 25. You add them together, you get 74.
All right, that's how that works. Multiplying a number by its conjugate will be a real number. It'll be a real number, not an imaginary number. So that's kind of cool. So that is the video of the conjugate. So that is there in Buzz if you need to say that. Let's look at the assignment that goes with the first lesson. Simplify. So it's all about simplifying. The square root of negative 121. You have 4 choices. Simplify. This is a little trickier, negative 48. See, 121, you can take the square root of 121, it's 11, but how does the answer look? This one, you're going to simplify 3 times 16. 3 times 16 is 48. 16, we can take the square root, it's 4. I to the 38th power. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way to 38, and figure out which one of those is that the same as. Simplify 6 plus the square root of negative 80. Really, this is no harder than this up here, simplifying the square root of negative 48, because you don't do anything with the real part. The real part is still going to be 6 plus. See how nothing changes? You're just simplifying the imaginary part. Simplify I to the 12th. 1, 2, 3, 4, 5, 6, 7, 8. All right. And what is the conjugate of 13 minus 11i? If you need to back up one and watch that video again, but that should be, don't make this hard. 13 minus 11i has a conjugate. What is the conjugate? All right, 6 questions. Let's look at the next lesson because this is where it gets fun. Operations on complex numbers. All right, so after learning about imaginary numbers, you may be wondering what their purpose is. I mean, while they're called imaginary numbers, they are anything but imaginary. Applications of complex numbers can be found in infrastructure on suspension bridges, designing airplanes, electricity. There's a lot of imaginary calculations. So we're going to talk about how the associative, commutative, and distributive properties can be used when performing operations on complex numbers. So let's review adding and subtracting complex numbers. We need to review combining like terms. Definitely combining like terms. So here, I'm going to write this one down. So here's the example written down. 7x squared plus 3x minus 5 plus 2x squared minus 4x plus 9. So when we simplify this, we can only simplify like terms. And this is not talking about terms that like each other. They may hate each other. I don't care. But they're the same type of term. They're like each other. Since this has an x squared, it's not like its neighbor. This guy don't have an x squared. All he's got is an x. And this guy don't even have an x. So he's not like him either. But this guy down here, they have something in common. They both have an x squared. He's only got an x and nothing down here. So since these guys have something in common, they are like terms. They are like each other. So we can take 7x squared plus 2x squared, and we have 9x squared. So we've combined that one and put them together because they're buddies. They're both x squared kind of guys. Now what are we looking at? Well, if we look at the next ones, we got 3x right there. Now, this guy, he does not deal in x's. He has nothing. He doesn't even know what an x is. He's just a number. This guy's already gone. This one has an x, and this one doesn't know what that is. So we have a 3x minus a 4x. So 3 minus 4, just minus an x, which now leaves us with just the numbers. These are just the number guys. They're just numbers. -5 plus 9. This is our elementary school kids because we're just taking numbers and putting them together. -5 plus 9. So this is the same thing as the original. Same thing, just simplified. That's going to be important because when we have like terms with complex numbers, let's say I've got 7 minus 3i plus 4 plus 5i. Real numbers don't get along with fake numbers. They're like, dude, you're not even real. don't hang out with me. Real numbers like to hang out with real numbers. 7 plus 4. Imaginary numbers like to hang out with other imaginary numbers. This negative 3i guy is going to hang out with this 5i guy. Negative 3i plus 5i. That is the answer. It's the same thing as this. This was actually addition because we added them together. We had this number and this number, and we added them together. It's two complex numbers, right? A complex number has a real part and imaginary part, like we learned right over here. So this is 7 minus 3i being added to 4 plus 5i. We add the real parts together, and we add the imaginary parts together. That's how we do addition with complex numbers. We cannot add the real to the imaginary. All right, got that in your notes? Does that make sense? This is important. Don't mess this up. Real numbers don't hang out with imaginary guys because they're way too fake. I ain't hanging out with you fake people. I'm hanging out with real people. All right. So that was combining like terms, their example. So the same concept goes with complex numbers. The real number and imaginary number. If we have 6 plus 8i being added to 3 plus 2i, the 6 plus 3 can be put together because that's the real part. The 8i and the 2i can be put together because that's the imaginary part. So the answer is 9 plus 10i. 6 plus 3 is 9. 8i plus 2i is 10i. 9 plus 2i. All right, let's look at subtraction. Now, subtraction, you got to remember, there's parentheses, so that negative has to be negative 10 and negative 4i.
You've combined expressions many times before, such as when you were combining polynomials and when you were combining radicals. The process for complex numbers is the same. Begin by distributing any coefficients. No integer or variables appear before either set of parentheses. Consequently, an understood 1 is put in its place. When 1 is distributed to the complex number within the first set of parentheses, the parts within are unchanged. However, a negative 1 is being distributed to the complex number within the second set of parentheses. This will change the signs on both the real number and imaginary number which follow. Now you can identify and combine like parts. The 12 and the minus 10 can combine because they're both real numbers, and the 3i and 4i can combine because they're both imaginary numbers. As you can see, combining complex numbers is very similar to adding and subtracting polynomials.
All right, so see what they did there? They start with these numbers. The real numbers subtract. 12 minus 10. We're subtracting the real from the real. Let me get that out of the way. Yeah, it's going to be in our way. 3i minus negative 4i. So that's why it ends up with 7i. Real from real. Here's another one that's a little bit different. We got 2 plus the square root of 121 plus the square root of negative 9. Negative 121, negative 9. So we're going to do some more work before we can do our addition there. So let's look at how they did this one.
A lot of students would see this expression and want to add negative 121 and negative 9 right away. But remember, radicals must be simplified into like terms before they may be added or subtracted. That simplification process begins by factoring the imaginary number from all radicals with a negative radicand. Now that the imaginary numbers have been factored, simplify the remaining radicals if possible. Well, that worked out nicely. All that's left is a real number part and 2 imaginary terms, which may be combined easily by adding the coefficients.
All right, so they made a good point there that we probably should review just to make sure we don't make that mistake, because it's an easy mistake to make. All right, this is a mistake that's real easy. I'll go ahead and turn it over, start a fresh page. We might want to, if we have 3 plus the square root of 4 plus the, and I'm not putting any imaginary numbers. These are all real numbers. Okay. Some of you might want to say this is 3 plus the square root of 20. I just took those and added them together. They're both under the square root. I added them together. 4 plus 16. Just put up here. No, you cannot do that. You cannot do that. This actually is a number. 3 square root of 4 is 2. Square root of 16 is 4. So just assuming the positives, because it's also -2 and -4. But so this would be like 9, right? Because we would just take those numbers. If, let's do this. 3 plus the square root of 5 plus the square root of 5. Now these are simplified. We can't take the square root of 5. It's not an integer. It's a decimal number. But since these are both the square root of 5, we can combine this. There's 1 square root of 5 here and 1 square root of 5 there. So this is the same as 3 plus 2 square roots of 5. It's kind of like having 3 plus x plus x. We got 3 plus 2x. But if these are not the same, we cannot do that. Same. If those are the same, then we can do that. Just add them together. Which means if we had 3 square roots of 7 plus 2 square roots of 7, that's 5 square roots of 7. Because this 3 times the square root of 7 means there's 3 of them. Right? So I got the square root of 7 plus square root of 7 plus square root of 7. Over here is 2 more. So altogether, I've got 5 square roots of 7 because there's 3 of them here, there's 2 of them here, there's 5 of them there. That is legal to do. But you have to, again, have the same. You cannot do it if they're not the same. So I just want to put that in there because somebody's going to make that mistake. And I'm trying to catch it before you make it rather than talk about afterwards. So here's an example where they have 4 square roots of -24 plus the square root of -150. So first thing you do is take the imaginary number out. -1 times 24, -1 times 150. Okay. Then you simplify from there. Square root of 24 simplifies to 4 times 6. And the square root of 4 is 2. So now you got the 4i that's out front times 2. So you got 8i. After the plus, you got 150, which is 25 times 6. The square root of 25 is 5. So you got 5i square root of 6. Now you've got 8i square root of 6 plus 5i square root of 6. Oh, look, these are the same. They're both the square root of 6. So we can put them together and have 13i square root of 6. Since they both have the square root of 6. It's kind of like having the same variable. You can combine them. They are like terms, so we can add them together. Great example to have in your notes right there. Great example. And they'll walk you through every step that you can put right there in your notes. All right, let's look at page 2. Multiplying complex numbers. Okay, multiplying is a whole different ballgame. We like multiplying. So let's look at what was the example they did. We'll do that one. Square root of 12, square root of negative 12, sorry. Times the square root of negative 5. If we're multiplying, we can combine those. But first, number one step, let's take out these negatives. So that's the same as negative 1 times the square root of 12, positive 12, times square root of negative 1 times the square root of 5. So we just took the negatives out separately. This is the same as these two. This one's the same as these two. Now we've got the square root of 1 times I'm sorry. This was a negative. I have to pull out the negative. I wasn't pulling out just a 1. I'm pulling out a negative 1. So this is a positive 12 now. But look what we have. Square root of negative 1 times the square root of negative 1. So that just equals negative 1. Because this is I and this is I. So really that is I squared. Because we got I times I. That's I squared. I squared is negative 1. And with these, when we're multiplying, we can combine those to be 12 times 5. Negative square root of 60. 12 times 5 is 60. And then we try to simplify from there. How can we simplify 60 to get square roots out of there? All right, so if you don't know how, I'm going to break this down to its simplest way. If we're trying to factor out 60, let's break 60 out to the smallest possible numbers. So 60 is the same as 2 times 30. 2 doesn't change. 30 breaks down to 2 times 15. Okay, this doesn't have a 2 in it anymore, but it is the same as 3 times 5. So the factors of 60 are right here. 2, 2, 3, 5. 2 times 2 times 3 times 5. That equals 60. Because we just kept dividing 2 out until we couldn't, and then we divided 3 out, and now nothing can be divided from those numbers. Those are prime numbers. Well, every time there's a pair, we know we can take the square root of that then. So 4, those should go together. These are done. There's only 1. If there was 2, we'd put them there. So we can do this as 4 times 15. So that equals negative the square root of 4 times the square root of 15. Because I broke it down to the smallest possible numbers. And I found there was 2 2s. So this 2 will come out. The square root of 4 is 2. And that's as simple as it gets. 15 doesn't break down anymore because that's 3 and 5. But 2 times 2, oh, that's a 4. So we can take the square root of 4. So that is the answer to this problem right here. Square root of negative 12 times the square root of negative 5 is negative 2 square roots of 15. Let's see if I can straighten that up a little bit. All right, I'll give you a second if you're writing that in your notes. It's a good example. And even though it started as 2 numbers, to which these are imaginary numbers, we can't take the square root of negative 12 because it's a negative number. We cannot take the square root of negative 5. It's a negative number. Those are imaginary numbers. But when we multiply them together, we get a real number. You want to see what that number is? Let's check it out because it is a real number. So let's put it up here on our screen and see what that number is. Okay, so it's negative 2 times the square root of 15. So let's take, I didn't want to make that bigger. The square root of 15, that's the square root of 15. And we're taking it times negative 2. Times 2, times negative 2. So that's what that number is. Negative 7.74596669241. So it continues on and on and on. The calculator just stops at that number, but it keeps going. but that is a real number. So this has a real number solution, and the number is negative 7.7459 onward. It's not imaginary. That's not an imaginary solution because there's no I. There's no square root of negative 1. That went away when we multiplied those together. All right, so here they're finding those prime factors just like we did. The 2, the 3, the 2, the 5. So 2 times 2 times 3 times 5. And they end up with 2i square roots of 15. Okay, prime factors, perfect square factors. What if you had multiplied the radicands before factoring? Oh, there you go. So what if we multiplied negative 12 times negative 5? We would have got the answer wrong because negative times negative is 60. So we would just be simplifying the square root of 60. We would have forgotten there's a negative out front. You have to factor the negative 1 out first. You have to factor that out. Because if we just said, oh, well, this is the same as negative 12 times negative 5, all underneath there, that's a positive. So instead of finding negative square root of 60, we would have been using positive square root of 60, and we would have missed that right there. We said equals positive 2 square roots of 15. And that would be wrong. So always do this step first. Pull the negative 1 out there so you don't lose that part of your solution. This is wrong. This is correct. Oh, we have another one. Oh, this gets a little more complicated. We've got the square root of negative 3 and then parentheses a complex number. So this is a complex number. Oh, let me point that out. Because you're looking at that going, that's not a complex number, Mr. Brock. Square root of negative 3. That is the complex number. What's the real part? 0. That's the complex number. This could also be I square roots of 3, right? Or square root of 3i. But if you just see the imaginary part, like if I just have 2i, that's an imaginary number because it's 0 plus 2i. Its conjugate would be 0 minus 2i. So it'd be 2i and negative 2i. That's the conjugates. I said they always come in pairs. But when you just see this, that means there's a 0 for the real part. All right, so this video has multiplying two complex numbers together. 0 plus the square root of negative 3 and 12 plus the square root of negative 6.
In this problem, you are asked to simplify the square root of negative 3 times 12 plus square root of negative 6. Begin by factoring imaginary numbers. Now distribute the imaginary number outside the radical. Distributing the imaginary number requires multiplying both I and the radical by each part of the complex number within the parentheses. Next, simplify the radicands where possible. Finally, substitute negative 1 for I squared. Can this expression be simplified further? No. Typically, complex numbers are written with the real number part first and the imaginary number part second. You may switch the order of these two parts so long as you take the sign in front along for the ride.
Taking the sign for a ride. But there you go. Negative 3 square roots of 2 plus 12i square roots of 3. So that's a complex number. This is the real part. This is the imaginary part. But the first thing they had to do was pull that negative 1, square root of negative 1, out of both terms. Otherwise, you'd miss this negative out front. Your answer would be incorrect. All right. Now that you know how to multiply negative radicands, let's multiply two complex numbers. All right, so I'm going to put this on paper so we can do a good example of this. Before we run out of time, class time is getting low here. Okay, so this is the type of problems you'll see, multiplying two complex numbers. You're just distributing because you have parentheses, so you have to distribute just like we do anytime that we, think of it when we had 6 minus 3x and 5 plus 3x, you just distribute. So this will be multiplied by both of those terms. And then after we do that, then we take the second term and we multiply it times both terms. So when we multiply the first term, 6 times 5 is 30. Okay, that's a real number. 6 times 5. Now 6 times 9i, 6 times 9 is 54i. See, that's going to be an imaginary number. Then we got negative 3i times 5. Negative 3 times 5, negative 15i, right? Negative 3i times 5. And this last part is negative 3i times 9i. Negative 3 times 9 is negative 27. I times I is I squared. I wrote the imaginary part in blue and the real part in red. But you're saying, Mr. Brock, that's got an I. Shouldn't that be in blue? No, it's got an I squared. I squared equals negative 1. So this is negative 27 times negative 1. So when we're simplifying, plus 54i minus 15i minus 27 times negative 1. Okay, so let's do that. If we have a negative times a negative, so that's the same as plus 27. Right? That's really what that is. So 30 plus 27 is 57. 54i minus 15i. So that's our answer. The answer has a real part and an imaginary part. Multiplying together, we just distribute and then simplify. Don't make that overly difficult. It is that simple. You just got to keep your eyes straight. So 57 plus 39i. They get the same thing. If you want to watch them do the steps. Conjugates. If you multiply something times its conjugate, you get rid of the imaginary number. Right here, multiplying the complex number times its conjugate. It goes away, the imaginary part. It'll go away real nicely. So let's do that one real quick. That'll be our last problem because we're down to the lesson summary. Okay, I have 8 plus 3i, and I'm going to multiply it by its conjugate. Well, we know the conjugate is 8 minus 3i, because that's how conjugate works. Exact same numbers, you just change the sign of the imaginary part. 8 times 8 is 64. 8 times negative 3i is negative 24i. Positive 3i times 8 is plus 24i. 3i times negative 3i is minus 9i squared. Again, so this is the same as negative 9 times negative 1 because I squared is negative 1. So this would be 64 minus 24i plus 24i. That's 0. Negative 9 times negative 1. This is plus 9. So all of this just equals 73. When you multiply 8 plus 3i times its conjugate, 8 minus 3i, the answer is 73. So don't overcomplicate that either. When you multiply something by its conjugate, it's a real number. It's a real number. It's not imaginary. So the conjugate's very, very useful to get rid of imaginary numbers. What does it simplify to? 73.
So when I hear you complain in mine,
That's what we came up with. That was our answer.
a gizmo that we're all going to do together, how gross.
Okay, lesson summary. Adding and subtracting, you just add and subtract the real numbers and add and subtract the imaginary numbers. If you have numbers like this, they square root of negative 121, you have to pull the negative out first. Multiplying, you use the distributive property, and remember, I squared turns into negative 1. So you have some practice problems.
What is that hyperbole?
Simplify. Simplify this. 12 plus 9.
You're
Well, that's going to be 21.
so
Negative 3i plus 2i. It's going to be negative I. You just combine the real parts and combine the imaginary parts. There's 5 of those. Here's another set of problems. Simplify and match them to the answers. Square root of negative 3 times the square root of positive 7. So this is I square root of 3 times 7. So it's I square root of 21. It's going to be right there. I square root of 21. All right. And so there's here's another page of problems over here. 6 questions. Simplify. Add those together, which means you probably are going to have to simplify to negative 50 to negative 1 times the square root of 50. 50 is 25 times 2. Square root of 25 is 5. So a 5 will come out of that. This is 36 times 2. 6 will come out of that. So simplifying is the real challenge on these. Can you simplify those? And if you can get them both to be the same square root, then you can add them together. So, all right. Let's look at the assignment that goes with the second one, and we'll be done. Simplify this expression. Adding. Real adds with real. Imaginary goes with imaginary. Here's the subtraction problem. Make sure you're subtracting the 8 and subtracting the negative 3i from its other parts. Here's a multiplication problem. Here's another multiplication problem. And here's a multiplication problem with conjugates. With conjugates, that tells you the answer is either 16 or 34 because there should not be any imaginary part. When you multiply 2 conjugates, it's a real answer. 5 problems. That's it. 5 problems. So, imaginary numbers, complex numbers have that imaginary piece. If you get confused on that, we've got class Wednesday and Friday this week. So you can come to class. So that means don't wait till Sunday to do this. Start it earlier in the week. Make sure you understand. Because if you don't, you can always come to class on Wednesday and say, okay, I'm lost, Mr. Brock. I thought I had it, and now it's gone. It's gone. Can you help me? Yes, absolutely. But if you wait till Sunday, I'm not going to get on Sunday night and help you. So. But don't make it overly, don't overthink it. Don't make it overly hard. It is not bad if you just keep it imaginary parts and real parts straight in your head. Don't do anything just against the rules. Real adds to real, subtracts from real, imaginary and imaginary, and multiplying kind of changes everything. So if you have to be in class Wednesday, Friday, we're here twice this week. If you don't have to be in class but are confused about this, come see me anyway. You won't have to stay the whole class because if your grade's over 70, it's optional for you to be there to start with. So, all right, guys, that's it for class. We just had a few minutes left anyway. So go enjoy the rest of your week and enjoy playing with your imaginary numbers. See ya.